Alright, Redshift. First of all, you need to be able to understand what's called the Doppler effect. So, the definition of the Doppler effect is the apparent change in frequency of a wave if there is relative motion between a sender of a signal and a receiver. Alright? So the observer and whatever's transmitting the signal. But it's a relative change in frequency. The best example is if, for example, an ambulance were driving past you. You're standing on the side of a road and an ambulance drives past. Now, before you think about what you'd hear when the ambulance drives past you, if you were standing on the road stationary and the ambulance was parked next to you, also stationary, and it switched on its siren, you would hear the siren of the ambulance like you have on a numerous occasion, and you will hear the same sound constantly. It will have a certain pitch. Remember, frequency of a sound wave is its pitch. So it'll either be high-pitched or it'll be low-pitched, all right? Deep or very high. But it will always be the same if you're not moving and the ambulance is not moving. Now, you may not have thought about it when you've seen it, and the next time you actually see an ambulance driving past, maybe just stop and think, does it do that? Because it will. If the ambulance is driving towards you, you know the person driving the ambulance is hearing the same sound non-stop because he's moving or she is moving with the ambulance, all right? But if you're standing stationary, and in this case the ambulance is moving towards you, and you draw those sound waves as lines, and the space obviously between them we know represents the frequency and wavelength. If the ambulance moves towards you, what technically happens is the waves appear to squash. So the sound waves that it's producing, although to the ambulance driver themselves are the same, because it's moving towards you, the waves that it's sending squash together, all right? Because every time it sends one, it comes a little bit closer to you. If those sound waves squash together, towards that sounds like a higher frequency sound. So higher frequency or lower wavelength. Now if you have a higher frequency sound, that is a higher pitch. So if an ambulance moves towards you, and again, go and just literally Google the sound of an ambulance driving past or a train, something that's emitting sound. On its way towards you, the sound waves squash, the frequency goes up, or the wavelength goes down, but the pitch goes up, so it sounds like it has a higher pitch, only because it's moving towards you. Now, as they're coming in, the waves squash, the ones behind obviously they'll move apart. Alternatively, if the ambulance were driving away from you, its siren is going off, the ambulance is driving away, you're stationary, but as it drives away, the sound waves that it's emitting, they're coming further and further apart, okay? They're elongating if you want, all right? The ones on the other side, obviously they're doing the opposite, but as the ambulance moves away, the sound gets further and further apart, the waves spread out more. That's a lower frequency or higher wavelength. If you have a lower frequency sound, you have a lower pitch sound. So an ambulance moving away will sound like it has a deeper sound, and it will be changing as it keeps moving away if it's a different speed. Alright? So this is the Doppler effect because it tells you how does the frequency of sound change or appear to change to us if something's moving towards or moving away. Alright? So moving towards, squash, frequency goes up, wavelength goes down. Moving away, frequency goes down, pitch goes down. How do we apply this to looking at objects in space? It's exactly the same. This effect uses sound waves from anything that emits sound. We can apply the same principle if we look at galaxies, for example, or stars in space. If there is a galaxy in space and I can observe this galaxy with a telescope, it will emit light from one of its billions of stars. The light will be sent from the galaxy at a specific wavelength. For example, if it was visible light, it could be yellow, for example, in the visible spectrum. It sends the light and we receive it on the Earth. If that galaxy is not moving, and we're not moving, then when we receive the light, we will get it exactly the same as the galaxy sent. Now, if the galaxy, on the other hand, is moving away, and it sends light here, and then moves away and keeps sending light, this light that eventually gets to us, as we said, if it's moving away, they will stretch. And if light stretches, frequency goes down, wavelength goes up. Now, if you look at the visible spectrum, that actually moves the wavelength towards the red part of the spectrum. Red has the longest wavelength, violet has the shortest. If an object emitting visible light, or any type of light, moves away, then the waves that we receive will be stretched. That means that its wavelength will have been shifted towards the red part of the visible spectrum. So this one, for moving away, is called redshift. It does not make the light look redder, necessarily. It may have started at yellow and become orange. That's not red light, it's just wavelength has moved closer to the red part of the spectrum, so it's being redshifted. Alright? So redshift is for any object moving away. Now, alternatively, if the galaxy on the other hand was moving towards, it sends the light out, it's moving towards us, the waves are going to be squashed as they receive on Earth, and if they're squashed, they have a higher frequency, lower wavelength, which is actually a shift, although we don't say violet, we say it's shifted closer to the blue part of the spectrum. So any object moving towards us has a higher frequency, we call that blue shift, because the light that we receive has been squashed, so it has a higher frequency which goes that way, lower wavelength. So blue shift is anything moving towards. Alright, and we know this because we have what we know is an absorption spectrum. We know if the light that is being emitted by the galaxy is made up of, for example, hydrogen, then the spectrum of hydrogen should look like this. The absorption spectrum will have black lines there, there, and there, at very specific wavelengths, as we know from the orbitals of the electrons absorbing radiation. Now, if what we receive on Earth looks like this is the original spectrum. If it wasn't moving, this is what we'd receive. What we do receive is this. Now, I can see very clearly this spectrum should be exactly the same as that. You can tell that it's from the same element. But what's happened is every single black line has been shifted slightly towards the red part of the spectrum. So what conclusion do you make? If it's the same spectrum, but all spectral lines have been pushed towards the red part, all of their wavelengths have increased, then it's redshifted. Now if it's redshifted, it must mean that that object in space is moving away. Alright? Alternative is true. Here's the original. Look at the black line that corresponds to this one, it's gone that way. Same for that one, they've all been shifted slightly towards the blue part of the spectrum, which means it's blue shifted. Their frequency has gone up, which means it's squashed. That tells me that the object is moving towards. Alright? So this is redshift for objects moving away, blue shift for them moving towards. This is the principle because the wavelengths and frequencies of light when they're received are either squashed, higher frequency, lower wavelength, or they're stretched, lower frequency, higher wavelength. That would either mean it shifts towards the red, if it's a longer wavelength because it's stretched and it's moved away, and if it's squashed it means it's moving towards, which is towards the blue, so it's blue shifted. Now, there's one more thing. If the object is moving away, then it's red shifted, okay? But if you receive a spectrum that is even more red shifted than another, then that means not only is it moving away, it's moving away faster. Because if this ambulance was coming towards you, you would hear the siren with a higher pitch. The waves would squash, it would be higher frequency, higher pitch. But if it moves towards you faster, it will be even higher pitch because it will squash even more. Alright? In this example of redshift, the object is moving away because the wavelength of the light that I receive on Earth has a longer wavelength and it's been stretched. That means it's towards the red, it's redshifted, it's moving away. But what if I received a spectrum that's changed those lines? This is the original that I expect, but it's been shifted even more. These ones have shifted even further than the one before. It's more redshifted, which means, yes, it's moving away, because redshift is moving away, but if it's more redshifted, then it must be moving away faster. Alright? And this is the evidence. If you put yourself, let's say the Earth is not at the center of the universe, but let's say it is for argument's sake, everything that you observe, pretty much, not everything, but almost everything that you observe, if you look in that direction and look at the galaxies over there, then you look in that direction and you check some galaxies over there, all of them seem to be moving away. Almost every object that you observe in the sky is redshifted, which means every object, for some reason, is moving away from the Earth. Alright? Now, if you take some that are a little bit closer, they're still moving away, but what we recognize is the further they are, from the Earth, the light that we receive is even more redshifted. That means the further away they are, the more redshifted they are, that must mean they're moving away faster. If objects further away are moving away faster, then there is one conclusion that can be made from that. Everything's moving away, but the further they are, the faster they're moving away. Maybe space itself is expanding. Alright? This is the evidence that supports the theory that the universe is expanding. Because if you're at the center and everything is moving away, but things on the edge move away faster. That happens, for example, if you drew some dots on a balloon, and the dots that you drew closest to the mouthpiece of the balloon, and then you had the dots on the edge of the balloon, and you blew up the balloon, the whole balloon is going to move away. It will expand, and all the dots will move away from each other. However, as the balloon expands, the dots that are further away from you are going to expand and move away even faster than the others. The one closest to your mouth, yes, they'll move away, but they'll move away a little bit. Those that were even further, they're going to move away even faster. That is literally expansion. So, this is what we saw. Everything we seem to look at in space was moving away because all the light that we received was redshifted. But the further away the objects were, the more redshifted their light was, so the faster they're moving away. And one conclusion that was made from that evidence was that maybe the universe itself is expanding.